Hi everyone, welcome to this lecture for ENES 102 on Unit 1. Today what we'll be talking about is introductory material for the course, which includes significant figures, an introduction to forces, force vectors, and real-world applications of those concepts. At the end of the lecture we'll do some practice problems to show you what types of problems you might experience related to this content in the ENES 102 course. Let's first talk about significant figures, everybody's favorite thing. Now, I'm sure a lot of you are big fans of Netflix and have watched almost every single video and show on there. So, as a result, I'm sure that you must have checked out one of the most famous movies of all, especially if you're interested in engineering. That movie is called Significant Figures, which I've seen before, and it truly is an excellent movie. Psych, I'm joking. This is one of the first jokes of the semester, and I hope you laughed, or at least are very sad at how bad it was. At least appreciate all of the effort it took for me to Photoshop the word significant into this so that it almost looks like it matches. Anyway, what are significant figures? Significant figures are essentially the digits of a number that are used to express it to the required degree of accuracy, starting from the first non-zero digit. Here you can see the rules below in this infographic. As you can see, the first zero before a decimal point is considered not significant and is there purely for cosmetic purposes. The next two zeros are also not significant because they're used only to locate the decimal point. The next things right here are all significant because the 4 and the 4 and the 5 are non-zero integers. These two digits right here are significant because they are between the non-zero numbers, and the last two digits are significant because they are zeros to the right of the decimal point. Now let's see how this applies to some examples. What I want you to do right now is take a minute. Using the table on the left, I want you to solve the problems on the right and determine how many significant figures problems A through E possess. I'll give you a moment. Okay, the first number, 0.0035, contains two significant figures because all of the zeros in the beginning are not significant and are instead considered leading zeros. Question B, 1.080, contains four significant figures because all of the numbers are pretty much significant. The one that's before the decimal point is considered significant, and all of the other ones are either interior or trailing significant figures. If we look at question C, 2371, that has four significant figures because all non-zero digits are significant. If we look at question D, that contains three sig figs because again, all non-zero digits are significant, rule number one. If we look at question E, that's a tricky one. That has only one significant figure because zeros to the right of a number without a decimal point are not considered significant. All right. Let's follow up and do just a few more examples before we move on to the next topic area. What I want you to do now is pause the slides and solve the next four numbers and determine how many significant figures they have. Okay, once you've taken a moment to solve these, let's look at the answers. The first number, 32.7, contains three significant figures. The following number, 0.00021 inches, contains 2 significant figures. The next number, 30,500, contains 3 significant figures. And the last number, 1.980, contains 4 significant figures. You might be wondering, Mike, why is this important? Well, I can tell you it's important because I see engineers make this mistake all the time, and it's actually really embarrassing, especially if you get up to higher levels of engineering. If you don't know your significant figures, you're going to look like a total fool when you're presenting to a professional audience. Let me give you an example of one of the most common mistakes I see students make all the time, particularly in ENES 100. Students will present their ideas for their oversand vehicle project, and they'll provide dimensions in which they plan to build their vehicle. And I can't tell you how many times I've seen students say, "Hey everyone, our vehicle is going to be 335.45567 millimeters by 275.000004 millimeters. That makes absolutely no sense. Why is that the case? It's because you do not nearly know that level of detail when you're building the OSV. For example, a human hair is 0.0889 millimeters in diameter. According to this presentation over here, they know and can manufacture their OSV with greater detail than the thickness of a single human hair. That's just not possible. Now, you might be wondering, Mike, sure, whatever. It's just, semantics. Who cares? They're not actually going to build it. They're just going to cut it off and build 275 millimeters. Well, that's true, but let me tell you a funny story. Once upon a time, there was a graduate research assistant. Could have been an undergrad, to be honest, just like you. He was told by his advisor that they needed to purchase some PVC pipe. They needed to purchase about 20 or 30 5-foot sections of PVC pipe. Now, if you're not really familiar with PVC pipe, essentially, it's just plastic tubing. Now, if you go into homedepot.com, you can see that about a 3/4 inch by 10-foot PVC section should only be about $3, give or take. What this graduate student didn't know was that he had to order the PVC on this special website. So he converted the feet into inches, which is what the website required, and he didn't really understand significant figures. So the website read 60.0000 inches. He's like, all right, that sounds good. That's 60 inches. All good to go. Took his professor's credit card, paid the bill, and everything was all good. Well, it turns out that if you try to develop PVC pipe and cut it to be that precise, essentially, the PVC pipe didn't cost $3 per pipe. It actually cost several $100s per pipe because of the accuracy required. Let's just say that this graduate research assistant wasn't employed much longer because he spent several $1,000s on PVC pipe when he should have actually spent only a couple dollars. Now, this is a true story, but it didn't happen to me. I won't tell you who it was, but you can imagine. Anyway, in ENES 102, we typically ask for 3 to 4 significant figures in your final answer. It's good practice to keep as many sig figs in your intermediary steps as you can, that way you avoid rounding errors. So only use significant figures in your final answer. And usually we don't include more than the 3 or 4 that we ask you for because, again, we don't know more than that level of accuracy. And as I was explaining in story time, it would cost a lot of money to build to such high levels of detail. So significant figures are not only an annoying part of science and engineering that matters in mastering engineering, but also that matters in the real world. So, let's now talk about forces. What kinds of forces are there? Well, everybody knows about the most important kind of force. The force is within each and every one of you, and it's up to you to harness it. In the force we must trust. That was my really bad Yoda impression. But anyway, joking aside, there are several different types of forces that we will talk about in this class. We'll have gravitational force, normal force, applied force, friction force, reactionary forces will be very big, spring force, and even tension. There may be many other things that we talk about, but you're going to get very familiar with working with different kinds of forces and all of these different problems that we'll do over the course of the semester. It's important to delineate that there's 2 different types of forces. There's forces in the x, and there's forces in the y. We refer to these types of forces as being linear forces. And there is actually another type of force that's called rotational forces, or, as we'll discuss later, and what we refer to them in this course, is rotational forces. And these are forces that cause something to rotate, and they are along what we call the z-axis. We'll discuss that in the next 2 lectures as we move forward in the course. But let's continue to talk about force here, and let's discuss units. In this class, we'll be dealing with newtons, which is a kilogram times meter per second squared. That'll be one of our very common units of force. Additionally, it's kind of good to put this into context and understand that 1 metric ton is 1,000 kilograms, just to give you some perspective. The other unit we'll be dealing a lot with in this class, and in the real world, is the unit of pounds of force. Sometimes you'll see kip, which refers to kilopounds or 1,000 pounds. And if you wanted to relate the one to the other, a kilogram is about 2.2 pounds. As you can see in the top right over here, this plate, which is 45 pounds, is about 20.4 kilograms. Now, pound is a weight, whereas kilogram is not. That's a mass. And this is something else that we always see students do and confuse in their presentations and write-ups. So make sure that you're using the right terminology for all of your different components. Now, it's going to be very important in this class and in the real world to be able to relate one unit to another unit so that you can contextualize and understand your answer. For example, let's look at this typical car. It's a Mazda, Zoom Zoom. How much do you think that car weighs? Or how many tons is this car? Take a minute and think about it. All right, what do you think? Does a car weigh more than a person, less than a person? Well, I guess it could depend. But let's hopefully say that a car weighs more than a typical person. And a typical car is about 2 metric tons, or 2,000 kilograms. What's the average person weigh? Well, the average person weighs 75 kilograms. So this will allow you to contextualize your answers a little bit. Now let's look at this cool example. How much do you think an elephant weighs? Does an elephant weigh more than a car or less than a car? Let's find out. An Asian elephant is about 6 tons. That's not just 1 car. That's not 2 cars. That's 3 cars is how much an Asian elephant's mass is equivalent to. That's insane. That's why if you ever see an elephant running towards your car, you better get the heck out of the way as fast as you can, because that's some dangerous stuff. Fun fact about elephants is an adult elephant can eat between 200 and 600 pounds of food a day. That's actually more than I weigh myself. So an Asian elephant eats 1 to 3 people per day. That's just crazy. One other fun fact for you. Did you know that the Newton is named after Sir Isaac Newton? And that the Newton is calibrated such that the weight of 1 single apple is equal to 1 Newton. I think that that's pretty cool. Now, why are we doing all this talking about units? You might be going, Mike, I understand all this stuff. Weight, newtons, duh, it's so easy. Well, based off all the answers I see in engineering classes, both at the freshman level and the senior level, you don't really understand it 100%. It's always good to make sure that you have a good conceptual understanding of units so that you can see if your answer makes sense. We gave a test to students at University of California, Berkeley in physics, and we asked them to calculate how fast this baby was moving given these conditions. One of the answers that I saw was the following: that the baby was going 60 meters per second. Well, if that were true, you would see wind shooting off of the baby, because that baby is the freaking fastest baby in the entire world and would be traveling 120 miles per hour. That student is going to one day try to become a doctor. Well, hopefully, they can understand that a baby can't physically travel 120 miles per hour. That's just not possible. So it's important to be able to understand your answer so that you know if it actually makes sense. Let's look at this in terms of ENES 102. You're going to oftentimes be finding the weight of a hanging object, perhaps a flower pot. If you calculate that the weight of the flowers hanging in this problem is 12,000 pounds, you're probably wrong. There's no way a flower pot could weigh 12,000 pounds. You would need a crane to hang that flower pot. Another common mistake I see people make is in the shape on the right. Later on in the course, we'll ask you to find the point where you could put your finger on this shape and balance it. I've seen many students answer this question and say, oh, well, I could balance this shape if I put my finger here. That's what the math says. Well, this little emoji guy in the top is pretty right. You should be scratching your head because there's no way you could balance the shape by not touching the shape at all. That makes no sense. So understand your answer. It's very, very important. Alright, now let's talk about vectors. What is a vector? Well, by definition, a vector has both magnitude, which gives you the magnitude or how strong something is or how long something is. Position could be 20 feet, a force could be 20 newtons, that's what's considered a magnitude. It's the length of the vector. But in addition to having a magnitude, we all know that a vector has to have a start and an endpoint, which is given to us via the direction. So fundamentally, a vector has both a magnitude and a direction. I'm sure we are all familiar with this concept. So vectors can always be broken down into components. So what does that mean? Well, if we take this vector, for example, this black arrow is pointing from the bottom left of the page to the upper right of the page. Well, if we wanted to, we could draw this green vector here and this blue vector here. And those two vectors would be equivalent to the black vector because they would have started and finished at the same point. We could take this a step further. We could actually break down the green vector further still into even more vectors. And we could do the same for the blue vector. If we did that, we could replace those two vectors and then we would have this. Well, at the end of the day, the summation of both of the green dotted line vectors and the blue dotted line vectors would be equivalent to the black line vector. Let's go even further. We could break those green vectors down to even further green vectors and those blue vectors down to even further blue vectors. Well, at the end of the day, all of this is equivalent to the first vector we drew because, again, all that a vector needs to have is a start and a finish, and all of these things would be equivalent. It's pretty cool. So, understanding force vectors, we also need to understand addition and subtraction. So if we have two vectors acting on a system, the green vector and the red vector, we will need to be able to do addition and subtraction. So in this particular case, if we wanted to add these two vectors together, we would move the tip of the red vector to touch the tail of the green vector, and the net resultant vector that would occur would be the f vector. Now if we use the traditional xy axes, as the x being the horizontal and the y being the vertical axes, then what we could find is that this f vector, which is the black net vector, is equal to the fx vector and the fy vector added together. We can solve for the f vector's magnitude by using the Pythagorean theorem, which will get us that the f vector is equal to the square root of the x vector squared plus the y vector squared. So this is about magnitudes. It's also important to understand directions of vectors, and this is where trig comes in. Fun fact about me is that I actually never took trigonometry in high school, or pre-calculus. I just skipped right into calculus. And I can tell you, looking back on that, that was probably a mistake. But anyway, I eventually learned sine, cosine, and tangent, which is the famous So Ka To Wa song. But really, this is pretty fundamental stuff that's going to be really important moving on later. I'm sure you've probably all seen this, and we'll do some examples. The point I want to make here is that make sure that your calculators are in degree mode, not radian mode. Because in this class, we'll be working with degrees. And this is really important because it'll make a very big difference in your answer. I see sometimes students hand in exams and they just forgot to change their calculator, and everything's wrong. Unfortunately, that's a fundamental mistake, and no partial credit can be given because it was so early on in the process. So, a little discussion of degrees versus radians, because to be totally honest with you, I never learned the unit circle or what radians were. So let me just explain that real fast before we get started. Well, if we look at a unit circle, we could say that 0 to 90 degrees is, as you see on the left. Well, in radians, as shown on the right, that would be 0 to pi over 2. If we went to the next stage, we would have 180 degrees, or pi, if we went from 0 all the way to the other side of the unit circle. Completing the rest of the circle, we can see in degrees that we have 270 at the bottom, and 360 degrees is one full revolution. One full revolution in radians is 2 pi. Well, you might be wondering, degrees, radians, what's all going on? This is all so confusing. What are they really? Well, to be honest, degrees and radians are just arbitrary units which are telling you the percentage of a circle that you've gone through. So they don't really have a true unit. They themselves are more or less percentages. Moving on, sine and cosine aren't fancy. As I'm saying, they're just ratios. What I want you to do now is take a look at these two triangles, the one on the left and the one on the right. Pause your video and figure out which will be greater for each triangle. And what I mean by that is, on the left triangle, will the value of the sine of the angle be greater, or will the value of the cosine be greater? And repeat the process for the triangle on the right as well. Pause your video, complete this exercise, and then you can start the video again. Okay, what we can tell is that the triangle on the left is tall and skinny. So the sine of that triangle is going to be of the angle theta in the bottom left is going to approach a value of 1. So when that happens, the triangle is tall and skinny and the sine is greater than the cosine. On the triangle on the right, we can tell that the cosine is going to be approaching a value of 1. And our triangle is short and fat, which means that the cosine is greater than the sine. Having this basic understanding of sine and cosine will help you check your force components later on. A lot of times I'll see students have a nearly vertical force where they'll say that the x component is actually much greater than the y component, and it's because they've done their angles backwards. So just using visual inspection with the math that we've discussed earlier, you're able to check your answers and really make sure that you're doing things correctly. Going back to our original force vector F, we showed that force vector F was a combination of Fx and Fy. In this case, if we have the angle B, or the angle beta, we can see that the sine of beta is equal to the opposite over the hypotenuse, which is Fx over F. If we follow that, we can do some math, and we can multiply F on both sides of that equation, and we would find that Fx is equal to F sine of beta. We can repeat the process for the cosine, and find that Fy is equal to F cosine of beta. This is how you determine the x and y components of the force. And this is going to be very important because throughout this course what we'll be doing is we'll be taking vectors that are in potentially multiple directions, in this case the x and the y, and we break them down to their constituent parts, the x and the y, so that we can add like things. This will become a lot more clear later on when we do some more practice problems, but in this particular case, it's just important to realize how you find the x and the y components and understand that the x component is not always going to be multiplied or found by multiplying f by the sine of beta. Sometimes you'll use cosine and vice versa for y. So just pay attention. A lot of times in this class you won't actually be given angles, but you'll be given a triangle. And the way that you compute the components of this force into the x and y components is actually to use something called similar triangles. Now, the way that this works is if your force here, in this case, is 35 newtons, it's directed upward and to the left, we know that that can be resolved into an x component and a y component. The x points to the left and the y points up. We're adding those two vectors together to get the up and to the left vector of 35 newtons. Well, how can we find fx and fy if we don't know the direction? Well, that's exactly where we have the similar triangle of 3, 4, 5. So what we can more or less do is we can do some math to show that fx is equal to 4 over 5 times 35. This effectively is coming from the fact that we have fx over 35. So we have fx over 35 is equal to 4 over 5. So as a result, pretty much, that's how we get this equation right here. We do the same for fy, and we get that fy over 35 is equal to 3 over 5. Therefore, by multiplying by 35 newtons on either side, we can compute fy is 21 newtons. Technically speaking, if you had been given a similar triangle, you could have back calculated and solved for theta and then used your typical way and said that, oh, well, fx is equal to 35 times the cosine of the angle and fy is equal to 35 times the sine of the angle. But one thing that's really important to kind of realize here is that the cosine of that angle, if you actually plug that in your calculator and did the math, you would find that it's exactly the same as the ratio of the triangle that we already showed, 4 over 5. So a lot of times we will be giving you similar triangles because that's going to be actually a faster and easier way for you to do the problem than to be giving you an actual angle. One other thing we'll note here before we move on is that vectors can also be represented in Cartesian vector form. F as a vector, or that little line over top of it, could be equal to fx I hat plus fy j hat plus fz k hat. In this case, our vector would have been shown as f 1 is equal to negative 28I, because our x was going to the left, plus 21J, or 21 newtons in the y. Now, this is really going to be much more important when we get into 3D statics, but it's at least important that you kind of understand this now as we move forward. So, more or less, there's all sorts of different ways to represent a vector. What we just showed was you had the 35 Newton vector at a 3, 4, 5 triangle angle. That's the same as showing the vector as 35 newtons inclined at an angle of 36.87 degrees, or it's the same as saying that we've got a 21 Newton force acting up and a 28 Newton force acting to the left at that particular spot. Again, you can work backwards and find the angles, the similar triangles, or the total vector from any of these particular cases, and all of them are valid and correct. Now that we've talked about forces and vectors, let's showcase a real-world example and show how these concepts can be applied to build massive structures, like the Great Pyramids of Giza. How tall do you think the Great Pyramids were? Taller than a skyscraper today? Well, the answer is that they're 455 feet tall. How does it compare to some more familiar structures? Well, to put this into context, Statue of Liberty is 305 feet tall, whereas the Golden Gate Bridge is 746 feet tall for a pylon, and probably one of the closest and tallest structures to us, the Washington Monument, stands 555 feet tall. So the fact that the pyramids were 455 feet tall, considering they were built thousands of years ago, is actually immensely impressive. How did the Egyptians build such massive structures without the use of cranes or energy or gasoline, things that we possess today and take for granted? Especially considering that each block weighs between 6.5 to 10 tons. If you imagine and look back to what we talked about before, that means they weigh not only as much as one car, not even as much as 2 cars, not even 3, not 4, but they weigh as much as 5 cars. That is huge. How could the Egyptians lift such massive things? Well, the answer lies in their ability to understand force vectors and to develop a very simple machine. By building a small ramp and inclining it at some angle theta, or a very small angle, and putting wood on top to act almost as like wheels or rollers, they were able to take the massive stone blocks with the weight shown in black here that's pointing straight down towards the center of the earth, and by putting it on the ramp, they were effectively able to break that force into 2 components. One that's perpendicular to the ramp, shown in blue, and one that's parallel to the ramp, shown in orange. By doing this, to move the block, they not only need to lift it up, but they actually can now push it up the ramp. And this only requires mg sine theta, or the component that's parallel to the ramp. This actually makes things extremely easy, because if you build your ramp in a proper way, for in this case, let's say 12 meters long, for every 1 meter of vertical rise, then you would have an angle of 5 degrees. And the sine of 5 degrees is a value of 1 over 12. So, to compute the force necessary to move this block, instead of applying 20,000 pounds to lift it vertically upward, they were able to take the F of 20,000 pounds and multiply that by the sine of theta, as 1/12 in this particular example, which gets them a force to move the block of only 1,600 pounds. That's about the force of 10 men. So if you have people pushing from behind and people pulling at the front, and perhaps even using animals, it actually becomes much more possible to move the block. Now, what's important to understand is that the total energy used remains the same throughout this process, and we'll discuss that more as we get into the machine lectures later on. Now let's discuss some practice problems, because not only is it important to understand how these concepts apply to the real world, but it'll be important to actually be able to do the math so that you can not only understand, but also design real-world systems. So let's look at this particular example here. Let's say that you're moving into your dormitory and you want to move in a really giant fridge, one with a TV on it and an ice maker, because those are very important to you. So you ask your buddy to come and help you push your refrigerator. So there's you, and you ask your friend, she comes, and she starts to help you, and you're having a bit of trouble, but the two of you combined are pushing your refrigerator into your room, and together you're applying these 2 forces. Your friend is applying a force of 500 newtons to the left, whereas you're applying a force of 100 newtons, directed at the angle shown right there. Well, what's the magnitude and direction of the resultant force of the two of you acting together? Take a minute and pause your video and try and solve this question. In a moment, we will go over the answer. Okay, let's show you how to do the answer to this problem. Effectively, what we need to do is we need to take the 500 Newton force, which is purely in the x direction, and we need to add that to the 100 Newton force, which is both in the x and the y direction. So how do we do that? Well, what we need to first do is we need to take the 100 Newton force, and we need to break that down into its x and y components. So to do that, we know that we've got a similar triangle of 3, 4, 5. That tells us that fx over 100 is equal to 3 over 5. So if we do the math there, that tells us that fx is equal to 60 newtons. If we look at solving for the fy component, we know that fy over 100 is 4 over 5. Doing the math, we calculate that fy is equal to 80 newtons. Now what we can do is we can sum up the forces in the x direction, because the sum of the forces in the x will be negative 500 newtons minus 60 newtons, which gets us a net force in the x direction of negative 560 newtons. And if we add up all of the forces in the y direction now, we get only one force, which is our 80 Newton force. Now it's important to recognize that whenever you take a force and you break it down into its two constituent vectors, that you never include the 100 Newton force anymore. That goes away because it's now broken into the 60 Newton force vector in the x and the 80 Newton force vector in the y. So as a result, this is our final answer for the x and y components of force acting in this question. And we can see that the net vector right here is going to be something that's going up and to the left. Now to find the magnitude, which is what the other part of this question is asking, we need to calculate the magnitude using Pythagorean theorem, which tells us that the square root of 560 squared, our x component, plus the square root of 80 squared is equal to 565.7 newtons. So, how do we find the direction? The way that we find the direction is by looking at our vector over here. We can see that we've got 80 newtons going in the y direction and 560 newtons in the x direction. We can actually use the tan to the negative 1 function to be able to compute this. So if we take the opposite of our angle shown in orange, which is right here, and we take the opposite, which is 80, we divide that by the adjacent side of 560, and we take tan to the negative 1, we can get an angle of 8 degrees. Technically speaking, it would also be totally fine to take your vector here, once you've got the magnitude, and essentially show something like was done on this 100 Newton vector, where you're showing the similar triangle of that particular force. Usually the question will tell you whether they want the answer in an angle form, degrees, or in terms of similar triangles. But this is usually the more common type of answer. Let's look at this next example problem. Let's say that you and your friend had a great deal of trouble moving the refrigerator into the building and found that after all your hard work, it didn't even fit into the elevator. Shucks! Now what you have to do is you actually rigged a couple of ropes to it, and you're going to pull it up the 7 floors of Oakland Hall and try and bring it into your dorm yourself. Well, let's say that you've got 3 people pulling on all these ropes. You've got F1, F2, and F3, and you want to figure out the magnitude of the resultant force acting on the refrigerator. How would you do this? Essentially, what you're going to do is you're going to take each of these forces, F1, F2, and F3, and resolve them into the x and y components. Then what you'll do is you'll add up all of the x components, and you'll add up all of the y components, and again you'll use Pythagorean theorem to solve for the net magnitude. What I recommend you do now is that you pause your video and you actually solve this problem on your own for some practice. And what I'll do is I'll move to the next slide and show you how to do the question by hand. And we'll do that in just a second. But I'll give you a minute or so to kind of pause the video and get your problem ready to at least attempt to do this problem on your own. Okay, so we're going to now solve the problem that we were just talking about, and I'm going to do it by hand so you can see kind of my step-by-step process of how this solution is going to go. Again, remember, you and your friends are trying to move your refrigerator up into your dorm, and you've attached 3 cables to the top of the refrigerator via this hook, and essentially 3 different people are pulling on the cables at the forces shown here. We can see that F2 has 600 newtons directed 45 degrees counterclockwise from the y-axis. We can see F1 is directed with a force of 800 newtons at 60 degrees above the x-axis, and we can see that F3 is directed at 650 newtons at a 5, 12, 13 similar triangle. Our question is to solve for the magnitude and the resultant force of all of the forces acting on the refrigerator. Essentially what we're going to do is we need to set up a sum of the forces in the x equation, and we need to set up a sum of the forces in the y equation. And we're going to take these 3 vectors here and we're going to break them down into those 2 components. So let's make this a little bit color-coded. We'll take the sum of the forces in the x and we'll define those as being the blue vectors. So F2 is going to have this x component pointing to the left. F1 is going to have this x component pointing to the right. And F3 is going to have this x component pointing to the right. If we look at the forces in the y direction, we will label them as being red forces. And we can see that F2 is going to be made up of this y component here. F1 is going to be made up of this y component right here. And F3 is a y component that goes down. So let's actually do the math here and draw these vectors out. What I'm now going to do is I'm going to pause the video, draw these 3 vectors here, and then we're going to do the math to solve. Okay, what I've now done is I've now drawn kind of what we have over here in this picture, but I've drawn them out a little bit more clearly so that we can kind of see things and do the math. So now what we need to do is let's look at this part right here, F2, because that's the first vector we see in the top left. We can see that F2 is comprised of a force vector going to the left and a force vector going up, and we're told that it's 45 degrees from the y. Well, what this tells us is that my picture is not to scale, but that this angle on the interior is also 45 degrees. So what we know is that the sine of 45 degrees is equal to the opposite side over the hypotenuse, which tells us this is equal to F2y over F2. So you can see if we multiply F2 over to the other side, we get that F2y is equal to a value of 600 times the sine of 45, which is going to be equal to 424.26. And that is going to be in the units of newtons because everything is in newtons. So we can again show that the cosine of 45 degrees is equal to the adjacent over the hypotenuse, which in this particular case is going to be equal to F2x over F2. This tells us that F2x is going to be equal to 600 times the cosine of 45, which, because the sine and the cosine are both equivalent, we get the value of 424.26 newtons. So this is all the work that we needed to do for F2. Resolving that into its x and y forces so that we can later plug those into our sum of the forces there. Now what we'll do is we'll look at this particular force F1, which we know is going to the right and up at a 60-degree angle. So how do we solve this? Well, using the strategy we just did before, we'll say that the sine of 60 degrees is going to be equal to the opposite over the hypotenuse, which in this case is going to be equal to F1y over F1. This tells us that F1y is going to be equal to 800 times the sine of 60, which is equal to 692.8 newtons. Following the same methodology, we'll do the cosine of 60 is equal to the adjacent over the hypotenuse, is equal to F1x over F1. This tells us that F1x is going to be equal to 800 times the cosine of 60 degrees. That's going to get us a value of 400 newtons. Now we've done everything we needed to do for F1 and F2. We have them in the x and y components. Now we need to look at F3, which we're not actually given an angle, we're given a similar triangle. The process is going to be more or less much the same. So when we look at this, what we see is we have 5, 12, 13 triangle. So what we want to try and solve for is let's start off with, say, F3x. So to solve for F3x, we know that F3x over 650 newtons is going to be equal to the x component of our similar triangle over our hypotenuse, 12/13. What we then do is we multiply both sides by 650. And this tells us that F3x is going to be equal to 600. Following the same procedure, but just skipping a step more or less, instead of writing this out, we'll say F3y is equal to 5 over 13 times 650. So that tells us that F3y is going to be equal to 250 newtons. Now we've done everything we need to do to break everything up into the constituent vectors in the x and the y direction. Now we need to do our sum of the forces. So when we sum the forces in the x direction, we will find that F3 was going to the right, that was positive 600 newtons. We look at F2, and actually F2 was going to the left. So it would have actually been good to say that this is negative 424.626 newtons. So we subtract that in our equation here. Then we look at F1. F1 is going to the right, so we assume that that's positive, because usually what you'll do is you'll draw your coordinate axes, x, y. You'll make that positive. We're good to go. So then we add plus 400 newtons here. So our sum of the forces in the x gets us 576 newtons. We'll follow the same procedure for the sum of the forces in the y. If we look, F3 is going down, so we say minus 250 newtons there. F2 is going up, so we say plus 424.26 newtons there. And F1 is also going up, that's positive, it's plus 692.8 newtons. When we add all of those numbers up, we get 867 newtons. So, to solve for F net, we know that that's going to be equal to the square root of fx squared plus fy squared. And again, these are both the net force in the x and the net force in the y. So that's going to be equal to the square root of 576 squared plus 867 squared. This gets us an answer of approximately 1,040 newtons, or if we wanted to simplify a bit, F net is approximately equal to 1 kilonewton. Now this question did not ask us to solve for the direction of our final net vector, but the way that you could have done that is we see that our net in the x is positive to the right and our net y is positive up. So essentially our F net, which there's not really a great spot to draw this, maybe right here, looks something like this. So we have F net is comprised of this 576 newtons in the x and this 867 newtons in the y. So we could have solved for theta by simply doing tan to the negative 1 of 867 over 576. And that would get us theta. And there you go. That is a pretty standard statics problem that involves you taking a multi-force system, resolving those forces down into their x and y components, and then summing them up in the x and y. This is an excellent first problem to do because, as you'll see as we move throughout the class, this is done over and over and over again, and these are going to be your best friends by the time this class is over. That concludes this lecture.